Hello everyone, I am Dr. Subhasish Saha, Assistant Professor in Physics, Department of HNS, MLR Institute of Technology, Hyderabad. So today is the third lecture of the ongoing topics crystallographic and material characterization. In last lectures I discussed about what is crystal systems, mostly give the idea about simple cubic, base center cubic, base center cubic. For that cases, what is the effective numbers of atoms is there in that cases, what is the atomic radius is there. Then we discuss about atomic packing factors, what is the concept is there for atomic packing factor for these three type of crystal structure, and what is coordination numbers. Those we will discuss in the last lectures. In today's lectures I will discuss mainly what is Miller indices, a Miller plane, and what is interplanar spacing. So these two topics today I will cover. First of all, what is Miller index and Miller planes? So already discussed that crystal structure is basically periodic arrangements of points which are connected by the some lines or imaginary lines. So there is some buildings is formed. There is a crystal structure. We can say there is a different sets of parallel planes are there. Okay, so there are different sets of parallel planes are there in crystal structures. So suppose in this case there is one plane, this one, and this one. These are all three planes. These are three parallel planes is there. Similarly, there is another parallel sets of plane, this one, and this one. So there are another sets of parallel plane. Next, along with that, we can say there is another sets of planes is there, this one, then this one, then this one also. So we can say crystal structure consists of different sets of parallel plane having their different orientation. So different orientations is there. So it is a different sets of parallel planes is there, and those are different orientation is also there. We can got the idea from this structure. Now what is Miller planes or what is Miller index? Now the orientations of a crystal plane with respect to crystallographic axis is determined by 3 points. Those in a plane, those are non-collinear to each other. Okay, going to the discuss. So several different planes are there, right? So what is the orientations of that plane with respect to crystallographic axis? That can be determined by 3 points on the crystal plane, and those points are non-collinear. If we got the idea about those 3 points, now how can we determine the Miller indices? Suppose we got the idea about these points, 3 points. Now if we got the idea about these 3 points, we can easily determine the intercept of the axis in terms of lattice parameters ABC. If we know the points, we can easily determine the intercept on the crystallographic axis. Now we take the reciprocal of these numbers and then reduce those numbers into 3 integers having the same ratio. That result gives you Miller index, that is determined by HKL. Okay, that is the name was given by the British crystallographer. He actually first discovered these things. That name is Miller. It will be little clear, and that plane associated with that plane is called Miller plane. Now it will be little clear from the next diagram actually how to determine the Miller index or Miller plane. This is some surface level idea how to do these things. Let's go to the in detail with an example. Suppose there is parallel sets of plane is there. So it is one of the plane. Suppose ABC one of the plane. This is OX, Y, OZ are the crystallographic axes. Now, so there are 3 points. So this plane intersect on along 3 axes. There is one point, there is another point, and this one is another point on the crystallographic axis. In these cases, if we know these 3 points, earlier discussed, if we know the points, if we got already the points, we can easily determine the intercept. What are the intercept? If we got the intercept, then we can take the reciprocal of this intercept. Intercept is in this case, that is along x-axis edge length is a, so we can say 4a. Along y-axis it is only b, and in case of z-axis it is 2c. So these are the intercept. Now if we take the reciprocal of these things, that will come 1 by 4, 1 by 1 and 1 by 2. Take this reciprocal. Now multiply these things with LCD. Okay, if we multiply those things with LCD, is the, and it make it integer, then what will come? If we suppose what is the LCD for this thing? In case of LCD, it's 4. If we multiply these things with 4, then it will come 1, 4 and 2. So this is the Miller indices for this plane. So that is the idea. Now take it another example. Suppose in this case intercept is given 2a, 3b, 4c. So reciprocal is this one, 1 by 2, 1 by 3, 1 by 2. Now LCD is basically, in this case LCD is 6, right? Because it is 1 by 2, 1 by 3 and again 1 by 2. LCD is 6. If we multiply these things with the LCD 6, then it will, if we multiply it with 6, then it will come 3, it will give 2 and again 3. So Miller plane is 3, 2, 3 and Miller index is 3, 2, 3 for this plane. So this is some example. Now come to the some features of this Miller planes. So what is this Miller index for this plane? Suppose this is a cubic box and this plane, if you look this shaded blue color shaded plane, what is the Miller plane? In this case, this plane intersect along x-axis at 1. Okay, along y-axis there is no intercept. So, and along z-axis also there is no intercept. Intercept is no intercept, it is intercept at infinity. So what is the ratio? 1 by 1, then 1 by infinity and 1 by infinity. Intercept is at infinity. What is the intercept? 1, infinity, infinity. Then reciprocal of those things is this one. Then Miller planes will come, Miller index will come for this case 1, 0, 0. Similarly for this plane, look into this shaded. In this case, it intercept along x-axis at 1. For figure 2, it intercept along x-axis at 1, y-axis is also along 1 and z-axis intercept is at infinity. Now take the reciprocal 1 by 1, 1 by 1 and 1 by infinity. So what is the plane will come? Miller index will come, that will come, suppose we multiply these things, it will come 1, 1 or 0, right? So this is the Miller plane. This case also, how you got this 1 by 1, 1, 1, it is easy compared to these two others. So when the planes is not intercept with any axis, so that time we can consider the intercept is infinity. Okay, it intercept at infinity. Based on that we can determine the Miller planes and Miller indices. So already we discussed about these things. So these are the some features already discussed about these ideas. If suppose a parallel plane to the axis has intercept at infinity, we will discuss all those things. And these already discussed. Now come to the next discussion is, suppose there are 3 points, those are not intercept on the crystallographic axis. Suppose there are, then how can we determine Miller planes in these cases? There are 3 points. Suppose P1 022, 202 and P3 is 212. These are not intercept on the crystallographic axis. That is not that easy diagram. It is a little bit different. In that case, we have to use that vector form. Okay, we already know that a vector identity is there. How to determine the? In this case, we have to solve this type of problem if it is not in collinear and those are not located on the crystallographic axis. In those cases, how to solve that type of problem and how to get the Miller plane or Miller indices. Suppose now in this case we have to deal with a little bit different way. Suppose this point we have to write it in the vector form 0 I cap 2 j cap plus 2 k cap. P2 point also determined by 2 I cap 0 j cap plus 2 k cap and P3 is also in this way. R1, R2, R3 got. Now suppose Now calculating the difference between these things. Suppose R is one point, arbitrary point on the plane, that is xi cap, yj cap and zk cap. Now then what is R minus R1? If you got R minus R1, it will become this. Then R2 minus R1 will come this, and R3 minus R1 will come this. If we determine these things, now we use these things, A dot B cross C. So these are the, it gives the volume about these things, and this will be A dot B cross C will be gives the 0. This is a condition you have to use, and if you use these conditions, from there we can easily reach here. Okay, in this equation we can use the determinant of this matrix, and from there we can reach to this equation, 4x plus 4y plus 2z equals to 12. Now intercept is located at, if we divide by these things, x by 3 plus y by 3 plus z by 6. So then what is these things? It will, intercept is these things, intercept is 3, 3, 6, then reciprocal is 1 by 3, 1 by 3, 1 by 6. If we multiply the 6, that is the LCD, then it will come 2, it is also 2, and this is 1. So this is the Miller index of this plane. So if this plane, there are 3 points is given on that, from there, if those are not on the intercept on the crystallography axis, in that case you have to solve that problem in different way. That is vector identity form you have to use, and from there you can determine the Miller planes. Now come to the concept of interplanar distance. So we already said that the crystal structure is contain different sets of parallel planes. Okay, that is different sets of parallel planes is there, having their different orientation, different planes having their different orientation is there. So to determine what is the distance, what is the smallest distance between two parallel planes, that is called interplanar spacing. So in that case, how to solve these things? We have to use, we have to determine these things. In this case, we have to determine the distance between two consecutive parallel planes. How to determine these things? Suppose there are 3 axes, OX, OY, OZ are 3 crystallographic axes which are mutually perpendicular to each other. There are 3 Cartesian coordinate axes. Now consider there are 2 planes. One plane is passing through the origin, which is not shown it here. Another plane is ABC. Okay, one plane is, suppose there are 3 axes is there. Okay, in that axis there is one plane is passing through this origin. Suppose in 2D nature, suppose there is one plane which is passing through the origin. There is, suppose there is 3 crystallographic axes, x, y and z. One plane is passing through the origin, another plane is this one. Now what is the smallest distance between these things? That is called interplanar spacing, that is d. So this is some idea. Suppose one plane is passing through the origin, another plane is, suppose another plane is this one, that is A, B, C, and another plane is passing through this origin. So these 2 planes are parallel with each other. Now we have to determine the smallest distance, that is d. Now how to determine those things? From this diagram you can see what is the intercept or what is the point is there. Along x-axis this is distance is a, so points is a by h, 0, 0, where h, k, l are the Miller indices for this plane. Now, and for what is the point for along b? It is 0, b by k, 0, and in case of c, that is 0, 0, cl. Okay, so these are these 3 points of for this plane ABC. H, K, L are the Miller plane. Now then from there we can got the idea about what is intercept. Okay, what is intercept? We can easily got these things. These are H, K, L are the Miller indices of the plane. The coordinates of the points ABC are these points A by H, 0, 0, 0, B by K, 0 and 0, 0, CL. These are the 3 points. Now ON is the distance from one plane to another plane, that is the perpendicular distance, that is interplanar spacing, that is denoted by d. and alpha, beta, gamma are the interaxial angles. Basically, the angle between this ON, angle between ON and along OX, that is alpha, and from that angle between ON and OY, that is beta, and angle between ON and OC, that is gamma. Those are three angles, alpha, beta, gamma, made by ON along three different crystallography axis. So now we have to determine what is cos alpha, cos beta, cos gamma. That is the direction cosine of the line ON. ON is the perpendicular distance. Suppose there are two planes. I already mentioned that there is one plane is passing through this, another plane is this one. That is, suppose intersect. These are the, that is the plane. Now it is the distance, that is the smallest perpendicular distance, that is D. Now this ON makes an angle along x axis, that is alpha, along y axis, that is beta, and along, that is y axis, that is z axis, along OZ with that is gamma. Those are the lattice parameters. Now if we know about these things, now we can easily determine the cos alpha, cos beta, cos gamma. Now from this we use this formula. This is the straight line property. If this is a perpendicular distance, right? So cos square alpha plus cos square beta plus cos square gamma equals to 1. That is a property of a straight line. We have to use this property. Now we have to determine the cos alpha. ONA, triangle ONA. Let's come to the previous diagram. Triangle ONA. What is cos alpha? This is the triangle. From this triangle, what is cos alpha value? So cos alpha value is ON by OA. That is ON by OA, cos alpha. So ON is the D, and OA is the A by H. So this means cos alpha will come ON is basically the distance D and OA is A by H. So what will come? That will gives the formula cos alpha basically DH by A. Similarly, from another triangle, suppose this is triangle ONB. From this triangle, suppose from this triangle ONB, from there we can get the cos beta also. We can get the cos beta also. What is cos beta will come? That is cos beta will come ON by OB. That will give D by OB is basically B by K. So from there cos what is cos beta will come? Cos beta will come D K by B. Similarly, from another triangle we can got cos gamma also. That is cos alpha, cos beta and cos gamma. Now substitute those three into equation 1. Then what will come? It will come this form. Now what is D will come? D will come in this form. D equals to this form. This is the formula will come. D square equals to A by H square by A square plus K square by B square plus L square by C square. Now in case of cubic systems where ABC are equal. So ABC are equal and that is equal, suppose it is A. So it will come D square equals to A square by H square K square plus A square. So DHK will come A root over of H square plus A square plus L square. So what is interplanar spacing? Interplanar spacing is the distance between two parallel planes. That is the consecutive planes, two parallel planes, and what is the smallest distance. So that is the interplanar spacing, and that is depends on the length of that plane ABC, or called lattice parameters, as well as Miller index. So if you know the Miller index of that plane and if you know A value, then we can easily determine the D value. That is some idea it's given about the interplanar spacing. So today I will stop it here. Next video I will discuss about defect. What is crystal defect and what are the types of crystal defects is there. In next lectures I will discuss about those things. Thank you.